Hi, I'm Debajit Ghosh. I lead the Android Sync team at Google, and I'm delighted to talk to you about how you can build push applications for the Android platform. You can view live notes and ask questions on the wave at the following URL. During this talk, we're going to cover how many Android applications access data in the cloud. One of the fundamental challenges for those applications is how do you keep data on the device fresh? How do you keep the data up to date? There are two basic techniques, polling and pushing. We're going to talk about each, and we're going to see, ultimately, you typically don't want to use polling in your applications. You want to use push. We're then going to go through the APIs for the new Android cloud-to-device messaging framework that we've announced here at Google I/O. And we're going to see how easy it is to build push applications on Android. We're going to go through the APIs in detail, go through design considerations, and then we're going to wrap up with the demo. Anybody here have an Android phone? OK, maybe that's not a fair question. Anybody here have two Android phones? Oh, what? These are tremendous devices. They've got incredible browsers, and they can run really powerful, very compelling applications. So the most interesting applications are those that access data in the cloud, giving you seamless access to your data wherever you are. You can have applications like mobile alerts. Your favorite hockey team just scored a goal in overtime and is moving on to the next round of the playoffs. And you want to know the second that happened. You can have send-to-phone applications. You're looking at a map. You're looking at driving directions. You're looking at driving directions on the desktop. But you don't want to be looking at driving directions on the desktop. You want the driving directions on your phone, where you can use navigation to get to where you want to go. With a simple click of a button, you can send that map, you can send a web page to your phone easily. There are background sync applications. You want to access your data, you want to make use of your data wherever you are, whether you're online or offline. You want that data to sync to your device transparently. And when you make changes to your data in the cloud, when you make changes on the web, you want to make sure that the latest data is reflected on your device as quickly as possible. Across all of these types of applications, there's one fundamental challenge. How do you keep data on your device fresh? How do you keep your data up to date? Well, there are two basic techniques, polling and pushing. Polling is a fairly simple to implement technique. In polling, your application periodically asks your server, hey, has anything changed? Is there any new data for me? It's pretty simple to implement. But a lot of times, the data in the cloud isn't changing that frequently. So polling can take a bit of a toll on a battery. This is because whenever you're accessing data, whenever you're using the data network, you're powering up the radio. When you use the radio, you're consuming power. Even when you're done accessing data, the radio stays on for a couple of seconds. So this can take a little bit of a toll on a battery. Polling is, however, completely appropriate for some types of content. If you have content that's actually changing constantly, like stock quotes, news headlines, and your application is tolerant to showing slightly stale data, you can poll very infrequently, and then when the user is actually starting to view that data, is trying to access that data, your application can refresh the data immediately. Let's take a look at the impact on a battery when you poll. This is one of the routine measurements that we take on the Android team. It shows a typical poll. In the baseline, when a device is idle, it might even have an open TCP connection with the server, but there's no data being transmitted or received. The baseline power draw is about 5 to 8 milliamps. But when you start accessing data, if you're reading data, that power usage can jump up to 115 milliamps. If you're writing data, transmitting data can be more expensive than reading. That power usage jumps up to 180, 200, or more milliamps. So for a short poll here, you might have consumed 0.5 milliamp hours. And that can add up. If your application is polling every 5 minutes, then that adds up to 144 milliamp hours. That's quite a bit of a battery. A battery typically gives you about 1,200 to 1,400 milliamp hours. So that's over 10% of a battery from one application that's polling every 5 minutes. If you scale back your polling to every 15 minutes, you do a bit better. You consume about 48 milliamp hours. So what does this mean? How does this affect our design? When do we want to poll? Well, like everything else in engineering, there's a trade-off. And here, there's a trade-off between freshness and efficiency. If you poll very frequently, you'll have very fresh data, but your application's not going to be as efficient. Poll less frequently, and your data is not going to be as fresh, but you'll be a little bit better on the battery. So let's take a step back. What is it that we ultimately want here? When do we want to poll? Well, typically, ultimately, we don't want to poll. We want to push. Push-based systems provide both freshness and efficiency, and they do that by only making use of data when it's useful. In a push system, an application or a service will establish and maintain a connection, a persistent connection, with a server in the cloud. And that allows that server in the cloud to send data to the application when something's actually changed. If you use an Android device, chances are you're already making use of push functionality. The Google Contacts, Calendar, and of course Gmail sync functionality that ships on many Android devices makes use of push. Google Voice makes use of push. And Android Market makes use of push, like Vic showed in his demo this morning. Anybody can implement a push-based system on the Android platform. The Android APIs, the SDK, allow anyone to run a background service to establish or maintain a connection. Have any of you tried to build a push-based system on Android? A couple of you. If you've tried, no doubt you've noticed that there's a couple of details to work through. There's some things that you have to make sure you do to make that push-based system work well, to work efficiently. So it can be somewhat tricky to implement. Well, I'm delighted to share with you all of the time and energy, all of the work that we've put into making push work for Google applications and opening it up to all of you as Android cloud-to-device messaging. Android cloud-to-device messaging is a new Google API that we're launching in labs. It's initially going to be available as a small trial to developers, and then we're going to open it up to all developers later this year. Android cloud-to-device messaging requires Android 2.2 to be on the device, as well as Android Market. Android Market is required simply for a technical requirement to make sure that the underlying cloud-to-device messaging functionality is there and present on the device. Of course, you have a choice. You have the freedom to deploy your application however you want, on Market or on your own website. Android cloud-to-device messaging makes use of the existing persistent connection that's already used to power push in Google applications. So that persistent connection is well amortized across a number of applications. With Android cloud-to-device messaging, your servers can send lightweight data messages to your applications on devices. And this is typically used to tell your application when something has changed. This is how you can tell your application, hey, now's a good time to sync. When an Android cloud-to-device message is received on the device, it's converted into an intent, which is well integrated with the rest of the Android platform. That intent is broadcast. It's actually broadcast specifically to your application through the use of permissions, and then that allows your application to do whatever it wants. With Android cloud-to-device messaging, if you want some UI component, your application supplies it. You can do whatever you want. If you want a notification, You can use the Android notification framework to put one up. But if you're working on a background sync application, you might not need any UI. All you're trying to do is make sure that data syncs transparently in the background. If you do want to have some kind of a UI, if you want to put up a notification, for example, typically what you do is you go ahead and fetch the new data first, then put up the notification. So that way, when the user selects the notification, they can immediately access the new data. Android cloud-to-device messaging is a best effort service. We try really, really hard to make sure that each and every message gets through. We store messages reliably for delivery to devices that might be having network problems, might be temporarily offline. But every once in a while, a message could get lost, could be delivered out of order, and it's just something that you need to keep in mind when you're designing your application to make sure you're robust to that. If you're like me, you like to know how things work. So let's go ahead and take a peek under the hood of how we built Android cloud-to-device messaging. First, we built out a set of servers to manage those persistent connections from all the Android devices. And we've scaled those servers so they can handle connections from each and every Android device. On the device, we have a background service that establishes and maintains that connection. Of course, we honor the background data setting and don't do this work if the user has deselected background data, indicating that they don't want any data to be consumed in the background. This service starts when the network first comes up. Once we first go ahead and establish that connection, we work really, really hard to make sure that that connection stays alive. We make use of application-level heartbeats to keep that connection alive. This is because on a wide area network, there's a couple of challenges. First, there are a lot of components on a wide area network, like NATs and IP load balancers, that try and detect idle connections and kill those connections. In addition, there's actually an interesting phenomena known as half-open connections that we've encountered on various networks. And with a half-open connection, an application might be able to send data in one direction, but it can't receive data in the other direction. So we use our heart beating protocol to detect when that happens and reconnect. We also do everything we can to make this connection as efficient as possible. This connection is SSL encrypted, and we've built a distributed, scalable SSL session resumption system. So that way, each time a device reconnects, it doesn't have to re-download a 2 to 3K SSL certificate. Whenever you have an open TCP connection, if there's no data being transmitted or received, there's minimal overhead. There's very little power consumption, as we saw. However, whenever you start accessing the radio, including for heartbeats, that draws power. So we've worked really hard to minimize our heartbeat frequency. We've actually tuned this for a lot of different networks to minimize that heartbeat frequency, making sure that the connection stays alive, but otherwise try and make sure that it's spaced out as much as possible. And we also minimize the number of concurrent connections that we establish and maintain on a device. For Android cloud-to-device messaging, each Android device just uses one persistent connection. Let's take a closer look at heartbeats. With heartbeats, when one side hasn't heard anything from the other side for some period of time, it'll go ahead and send a ping. The other side, upon receiving the ping, will send back an ACK, and when the originating side receives that ACK, it knows everything's cool, connection's alive. If, however, one side sends a ping and doesn't get back an ACK, it knows that the connection's dead and it needs to reconnect. To implement heartbeats, we use the Android alarm framework. We use this to schedule the initial heartbeat, and then whenever we receive any kind of data over that connection, we know that the connection's alive, and we cancel that pending heartbeat and reschedule it. When we actually do go ahead and issue a ping, we schedule an alarm to wait for the ACK to come back in a timely fashion. If it doesn't come back, we know the connection's dead, and we reconnect. And we actually have the same protocol on the server side. The server side can also initiate heartbeats. On the server side, since the servers can't reconnect to the devices are typically behind a NAT or something like that, we mainly use this to detect a dead connection and clean up some state. Let's go ahead and take a look at the overall life cycle for Android cloud-to-device messaging. There are 3 basic phases. First, up front, an application on a device will go ahead and enable Android cloud-to-device messaging. And it does this using a very simple registration API. And with this registration API, each application on a device gets a unique registration ID. When that application gets its registration ID, it sends that to its server. So that way the server can use that for sending messages. In the runtime portion, per message, when an application server wants to send a message, it issues a very simple HTTP post to some servers at Google. When the Google servers receive that HTTP post, they store the message and queue it for delivery, for reliable delivery to the device, and things are good to go. Then, if an application wants to disable push, if it wants to disable cloud-to-device messaging, it can use a simple unregister API. And you might do this if, for example, you have a background sync application and the user unselects the auto sync checkbox. Let's take a closer look at that runtime portion. Let's look at the life of a message. Here, an Android device already established a connection with our connection servers. An application server will go ahead and send that simple HTTP post to our cloud-to-device messaging front ends. We receive that request, store the message, route the request to the appropriate connection server that's housing a connection from the target device, which will go ahead and send the message to the device. At this point, 2 things will happen basically in parallel. First, that message will be converted into an intent, which is broadcast to wake up or start up an application. In addition, the device will acknowledge receipt of that message so we can clear that from our store. The application wakes up, and then it can go ahead and fetch its latest data from its application server. Overall, the design here is to make sure that the relevant state typically remains in the application server, not in the message. Let's take a look at some code. To register, your application makes use of a very simple intent-based API. You create an intent and populate it with a little bit of data. You populate it with information about your application, and you also provide it a role account that your application server is going to use when it sends messages. This role account has nothing to do with any of the accounts on the Android device. Again, this is a role account that your application server is going to use when it sends messages. Then you go ahead and call start service. And then sometime later, your application will receive an intent back with the registration ID. When you receive that registration ID, go ahead and send that to your application servers. The Android cloud-to-device messaging framework might reissue or rotate these registration IDs from time to time, so your intent receiver that's receiving these registration intents might be called again in the future. And if that happens, all you do is do the same thing that you did in the first place. Take that registration ID and send it to your server. Here's some code that shows you how you can go ahead and process that registration intent. You have an intent receiver on receive, check for that registration intent, and then go ahead and see whether or not you got a registration ID. If you did, cool, send it to your server. If you get back an error, then you should retry with some backoff. To send messages, your application servers send a very simple HTTP post. This request is authenticated using the AC2DM authentication token, which you typically grab once up front using the client login API and install into your servers. you include this authentication token in the authorization header. And then you also include a couple of URL encoded parameters. You include the registration ID for the target application and device. You include a collapse key, which controls how messages are delivered when a device is offline. And you can also specify an optional delay while idle parameter, as well as some small amount of payload in the form of arbitrary key value pairs. We're going to talk about each of these parameters in turn. When you issue that HTTP post, you'll typically get one of 3 response codes back: a 200, a 401, or a 503. If you get back a 401, that means that your authentication token is no longer valid. So you need to grab a new one. And this could happen if, for example, you change the password for your role account. If you get back a 503, then you should retry your request with backoff. And please honor any retry after headers that you receive. If you get back a 200, that means that your request was syntactically valid. And if you get an ID in the response, everything's cool. We got the message and are going to route it to a device. If, however, you get back an error, one of several things could have happened. If we start detecting an unusual or excessive amount of messaging from a sender in aggregate across devices, or from a sender to a specific device, then you'll hit some quota limits. And when you do that, you need to back off and try again later. If the registration ID that you supplied was invalid, or if the application requested unregistration, then we'll tell you that. And you need to wait until you get a new registration ID from the application before you try sending messages to that target device again. If the message you sent was too big, the payload is limited to being about 1K. Or if you didn't supply a collapse key, you need to fix these issues before you try again. When a message is received on a device, it's converted into an intent. That intent is broadcast, and through the use of permissions that your application defines and requests, that intent is sent only to your application. When that intent is broadcast, your application is woken up, or it's started. So that means that your application doesn't need to be sitting there running in the background. You don't need to have some service running continually. Your application will wake up. Any payload that you provided will be converted into the extras in the intent. And you can do whatever you need to do. If you're going to be doing anything non-trivial, typically you'll grab a wake lock. Don't forget to release the wake lock when you're done. And you'll do whatever processing you need to do in a service. And you can use the intent service API to simplify your work here. And that's it. That's all there is to the API. First, you call registration to get your registration ID. Next, in the runtime portion, you issue a simple HTTP post to send messages. And then, if your application chooses to not make use of push anymore, for example, if the user deselects autosync, you can unregister. It's a pretty simple API. We found that most developers who are trying out the API can get something up and running in the matter of hours. We're now going to talk about some of the options and design considerations you need to keep in mind when you're making use of Android cloud-to-device messaging. The first concept we're going to talk about is that of message collapse. When a device is offline for any period of time, we want to avoid message delivery explosion when that device comes online again. A lot of times, say in a mail application, one, you have new mail message is as good as any of the other ones. So if you're on a flight, when you come off the flight, you don't need to receive tens or hundreds of those messages. You just need one. And so when you send a message, you can supply a collapse key. And that collapse key controls how those messages are stored and delivered. Typically, you specify a collapse key to correspond with some topic or some feed, whatever, that is meaningful to your application, perhaps a URL that your application is going to hit to get its data. And when a message is sent to our servers with a collapse key, if there are any outstanding undelivered messages already stored under that collapse key, the new one will overwrite the previous ones. This really emphasizes the design principle of keeping your state in your server, not in the messages. And we find that this allows for very clean design. It allows you to decouple your messaging channel from, for instance, your synchronization channel. And that way, the same code that you use for, say, a manual refresh can make use of the synchronization channel as is, and all you're doing when you receive a cloud-to-device message is kick off that code. Let's take a look at how this works. Here we have a device that happens to be offline. It's on the proverbial airplane. Your application server, as usual, sends a cloud-to-device message to our front ends. We receive it, store it, but then we don't route it to any connection servers because the device is not connected. The application server sends a subsequent message under the same collapse key. We'll receive that message, and that new message will overwrite the previous message. You can specify whatever collapse key you want on a message-by-message basis, but there's a limitation. Each application can have at most 4 messages or 4 unique collapse keys outstanding at any given time. The next concept we're going to talk about is attenuation. We want to make sure that data on a device is fresh, but we also want to protect a user's battery. We want to protect the radio. Whenever a cloud-to-device message is received on a device, that fires up the radio. And we want to make sure that the radio isn't constantly firing up. So if we detect that a specific application is sending a high frequency of cloud-to-device messages, we'll let the first few of those through quickly. We want to make sure that things are fresh. But then we're going to start holding on to those messages for a short period of time to make sure that the radio is not firing constantly. Attenuation is done on an application on a collapse key basis. Let's take a look. Here we have an Android device, and it's connected to our connection servers. And the application server has already been sending a bunch of messages recently. It'll send a new message to our cloud device messaging front ends. We'll receive the message, store it, and send it to the connection server. At that point, we'll hold on to the message for a short period of time, and then we'll send it to the device. Attenuation is a way that we automatically try and protect battery and delay message delivery. There's also a technique that you can opt into to be even more aggressive about delaying messages. And that's by making use of the delay while idle feature. Each Android device tells our servers when their screen is on or off. It does this efficiently. And by knowing when a screen is off, we know that the device isn't actively being used. And there are certain classes of content where data changes very frequently, but might not be of much interest if the device isn't being used. For example, in a chat application, you might not care about the latest presence updates, which can change very frequently when the device is in your pocket. You might not care about your friend's latest location information, again, when the device is on a table or in your desk. And so on a message-by-message basis, your application servers can specify the delay while idle parameter. And when that's specified, our connection servers will hold on to one of these messages while the screen is off for the target device. And then it will deliver that message immediately as soon as the device becomes active again. Let's take a look. Here we have an Android device. It's connected to our connection servers, but the screen is off. It's asleep. the application server goes ahead and sends a message to our front ends, which, as usual, we store, route to the connection server. But at this point, the connection server is going to hold on to the message. It's going to hold on to the message until the device actually becomes active again. When the user starts using the device, turns the screen on, we'll then immediately send the message to the device. Now that we've taken a look at the APIs and all the design considerations, let's see what we can do when we put all this together and build some real applications. The first application we're going to talk about is the Google Chrome to Phone extension that Vic demoed this morning. And this is going to be one of the sample applications for Android cloud-to-device messaging. In fact, you can already see all of the code on code Google.com p Chrome to Phone. This is one of the sample applications. And the really great thing about this, in addition to being a really useful application, this is one of the things that I've wanted for a long time. The application was built by an engineer who was just kicking the tires on our API while he was on a flight. So he built this really quickly. And I think it really shows some of the really cool applications that you can build with cloud-to-device messaging. If you didn't see the keynote, the Google Chrome to Phone extension is a simple Chrome extension that allows you to send any web page or a map or a YouTube video or whatever from the web to your Android device. It's powered by, of course, a small Android application and also a very simple App Engine backend. Let's take a look at how this works. First, you go ahead and view some web page in Chrome. The user will then go ahead and click on the Chrome to Phone extension, which makes a request to the App Engine backend. The App Engine backend then issues a request through the Android cloud-to-device messaging service, which will go ahead and send the message to the target device. The user can then select a notification, or you can disable that and have automatic updates on the phone. And then the Android device will fire up the browser, go to the origin server, and get the latest data. If you want to look at this in more detail, you can go ahead and look at the open source example. The next demo we're going to take a look at is JumpNote. JumpNote is a fully featured two-way push sync notes sample application. It makes use of App Engine on the back end, and the web UI is powered by GWT. It's also going to be one of the open source sample applications that we ship with Android cloud-to-device messaging. And this will show you a couple of things. First, it'll show you how to make use of the Android Sync framework that we shipped in Android 2.0. In addition, it also shows you how to use the new Android cloud-to-device messaging framework to enable push sync for your sync applications. When the cloud-to-device message is received on the device, the intent receiver simply kicks off a sync, just calls the request sync API, and that's all it needs to do. And then sync happens as normal. Let's go ahead and take a look. So here I have the JumpNote application. There's no data here. And I'm going to go ahead and create a new note. We're going to go ahead and save the note. And now we're going to switch to the Elmo. And on the Elmo, we can see the JumpNote application running on the device. What's happening here? Well, when I clicked on Save, the GWT application saved the data in the App Engine data store. It then used the App Engine Task Queue API to send the HTTP post for the cloud-to-device messaging request. Our servers got that request, stored the message, routed the message to the right connection server, sent the message to the device, which converted to an intent, broadcast the intent. The JumpNote application woke up, did its sync, and all of that happened in far less time than I took to explain everything that was going on. Anyone here interested in trying out Android cloud-to-device messaging? Well, I'm delighted to tell you that we're launching Android cloud-to-device messaging in labs now, and we're accepting signups. If you want to find out more, if you want to read our documentation, see the open source code examples, or sign up, go ahead and visit code.google.com Android C2 DM. You can also Google search for that if you didn't grab the URL. During this talk, we've seen how many Android applications access data in the cloud. And to provide freshness for those applications, to be both fresh and efficient, we've seen that you want to use push to keep data on those devices fresh and up to date. And by using the Android cloud-to-device messaging framework, you can do that simply. Android cloud-to-device messaging makes building push applications simple, easy, and efficient. If you want to find out more, you can sign up now at code.google.com Android C2 DM. We're going to go ahead and switch over to the moderator link to look at any questions. If you also have questions, you can go up to the microphones and ask them at this time. Thank you. Are there any live questions? Go ahead.
I was wondering, what is the typical latency that you're experiencing?
I'm sorry, I couldn't hear the question.
What is the typical latency from the time that the server pushes the message to your server and the intent shows up on the phone?
It's typically on the order of seconds. It varies, obviously, depending on the network and both the network between your server and our servers and the network between our servers and the device. But it's pretty quick.
Okay.
Is there an API or a mechanism to go the other way around from the device back to the web to do something like two-way chat in the same manner?
Typically, what applications do is they'll just go ahead and make use of regular HTTP integration with their application servers.
Hi. Two questions. You said that you need 2.2 Froyo and the market for this right now. Mm-hmm. Does that mean support for the emulators will come in later?
I'm sorry, can you say that again?
What about support for emulators? Because you'll be needing 2.2 and the market?
The 2.2 SDK will provide support for this. So you can test out your applications on that SDK.
OK. And I had a second question. Does the code side also have code for the App Engine side of the code?
Yes, absolutely. That's fully featured. So the Chrome to Phone example has the Chrome extension, the Android application, and the App Engine backend. The JumpNote example has the GWT and App Engine samples as well as the Android applications. We're giving you everything.
OK, thanks.
Yeah, you said that if the phone is idle, the server will hold the message and won't deliver it until the phone is busy. So how would you define when the phone is idle? It is possible that the user they will run the application as a service in the background and leave it on the table, and then the screen got I'm turned off and things like that. So how would you define when the phone is idle? Because that service might be waiting for the messages.
The question was, I believe, How do you determine when a phone is idle?
Yes.
Is that the question? We do it based on whether or not the screen is off. If the screen has been off for some period of time, we deem that phone to be idle, inactive, because the user is not actually looking at anything on the phone.
But then again, like the application, it might run the service in the background, and the service might be waiting for the message.
If you don't want to use the delay while idle option, you don't have to. That's something that you can do for types of data where you want that behavior. Does that answer your question?
Can you come again, please?
I'm sorry, I'm having trouble hearing.
Oh, so can you explain it again for me, please? So if the service is waiting for the message, and then the screen is turn off, how can you avoid that situation?
So the question is, how do you avoid having your messages be delayed
Yes.
when the screen turns off?
Yes.
If you don't want that behavior, you don't specify the delay while idle parameter. That's an optional parameter.
Oh, I see. Thank you.
Sure.
Yes, hello. Is there any ability to push a message against a certain time zone or locality?
Let me repeat the question. The question was, is there a way to push a message to a certain time zone or locality?
Yeah, for instance, like a country specific or something of that sort.
Are you talking about localization?
Yes.
That's something that's going to be up to your application. So typically, again, what you're doing with these cloud device messages is sending something that tickles, wakes up your device, wakes up your application, so it can go ahead and do whatever it needs to do. There's no UI component inherent to Android cloud device messaging. That's something that your application supplies. Does that answer your question?
Yeah, more or less.
Hi. So you mentioned that it's only available in 2.2. And so for previous, right now, I think everybody don't have 2.2, right? And a lot of phones will not be upgraded to that. So would that be backported somehow? And what's your recommendation on dealing with older phones that do not have that version?
The question was, this functionality is only available for Android 2.2. Will this functionality be backported? The answer is no. This is one of the new features. There's a lot of new features. We're always trying to innovate. We're always trying to build out new functionality. This is one of the new features that's in Android 2.2.
OK, so in that case, we will just do polling as before. That's what we could do, right? That's what you recommend.
The question was, in that case, would do polling as before on older devices? Yeah, you do polling, or you can, again, from day one, anyone can build their own push-based system. So you could go ahead and build that if you wanted.
OK, and one more question. So do you provide a broadcast capability where right now you're just saying, oh, the phone has to register for that message, and then you will go and send it, right? But there's a way that for any phones that has registered that has installed my app, is that way I can just send a message to everyone and let them know about certain information?
The question was, is there any way to send a message that's broadcast to all devices? No, the registration ID is a per app, per device ID. It provides compartmentalization of apps and devices, so that way one sender can't send messages to another application. So there's no way to do that. You'd have to issue a series of cloud-to-device messages on your server side.
OK, thanks.
What are the quotas, and is pricing available?
I'm sorry, can you repeat the question?
Is the service free? Is there pricing available? Is there quota limitations of how many messages the application can send a day?
The question was, what is the pricing? The pricing is free. What are the limitations? There are quota limitations, and basically what we're trying to do is look out for excessive usage in aggregate by a sender or by a sender to a specific device. And if you find that you end up running into those into issues with that, we can discuss and talk about quotas.
Okay, thank you.
2 questions. One is there a way to specify a TTL for a message that it should not be delivered after a certain amount of time? So just in case the user is offline at that point in time, the message will expire after, let's say, 2 minutes. And after 2 minutes, it will not be delivered.
The question was, is there a way to specify a TTL on a message? The answer is no, not currently, but if that's some of the kind of functionality you're interested in, we'll take that as feedback.
OK, thank you.
In your example with polling every 5 minutes, you said that that could use 5 to 10% of your battery over a day with that operation. Can you describe what mechanisms you use with your cloud-to-device to reduce the impact of that communication on the battery life of the phone? For example, it responds within 2 seconds, but it knows when the screen's off and that kind of thing. How are you keeping the battery usage down?
I'm sorry, I'm having trouble with the audio. Can you repeat the question? You were talking about the...
I'm curious how you're keeping the battery usage down on your own cloud-to-device messaging infrastructure, because you know when the screen is on or off, and you're keeping track of things, and you have quick response to messages. How do you keep from using much power with that?
Well, the fundamental idea here is we have one connection. We amortize that connection across a lot of applications, and when there's no traffic being transmitted or received over that connection, there's very little power draw. And so what we've done is we actually space out our heartbeats to be much less frequent than every 5 minutes. We make sure that those heartbeats are spaced out pretty far apart. So for an idle device, for a device that's not getting any data, there's not much impact on battery. Of course, if you're going ahead and making more use, if there's a lot of messages that are coming down, then that will cause radio wake-ups. It will impact battery, and that's why we have features like attenuation, and that's also why we have features that you can opt into, like delay while idle, so that way for your application domain, you don't need to have messages sent to an otherwise idle device, so you can afford to have them be delayed.
Thank you.
So that said, if there was no data being used otherwise, there could be something like a 5-minute latency in the system? You mentioned 5-minute heartbeat.
The question was, that said, is there a 5-minute latency in the system? Not at all. The heartbeats are not 5 minutes, in fact. We have those heartbeats in place, and they're much less frequent than every 5 minutes, on the order of sometimes half an hour. And we have those heartbeats in place just to keep the connection alive, because once you've established that connection, you want to keep it alive, because reconnecting can be a bit more expensive. So we're just trying to keep that connection alive. While that connection is alive, messages will be sent very, very quickly. There shouldn't be on the order of 5-minute latency.
Do you have any plans, or is this compliant with OMA push specifications?
The question is there any integration here with OMA push? Are there any plans to integrate with OMA push? Not at this time.
So basically, if I have a push server, I cannot use it. I have to go through the one that Google sets up, correct?
If you want to use Android, the question was if you have a push server, you wouldn't be able to use that here. That's correct. You'd have to, if you want to make use of Android cloud-to-device messaging, you have to use the Android cloud-to-device messaging APIs. If you want to build out support for OMA push, this is Android. You can build the service on the application, or you can install, someone else has built one. You can install that on a device, and then that can go ahead and connect to the OMA push servers.
Thank you.
OK, you said that you amortize the connection across multiple applications. The default applications that are shipping out that are used by Google, which use push services, do those also use exactly this connection, or do they have a separate connection, and this is only for applications by developers?
The question was, is this the same connection that's used for the Google functionality, or is there a separate connection? This is the exact same connection. So we're using this functionality. We've been using this functionality since day one to enable push for Gmail, contacts, and calendar sync, for a lot of other functionality. And we're just basically opening this up to all of you now.
Is there a way for the user to specify that he's OK with a high frequency of updates during some period of the day, like in the morning, and then in the afternoon say, I want very few messages during this time?
The question was, is there a way to specify an application is OK with latency during certain periods of time and wants more freshness during other periods of time? There's nothing like that. That's something that you would, that's the kind of logic that you would build out in your application server at the point when you're issuing the messages.
Right, but if I was too frequent, Google would scale me back, right? If I send messages too frequently, then your servers will back off, right?
Right. The question was, if the application's sending too frequently, will Google scale that back? Yes, that's what we do with attenuation, and there's no way to specify, hints or policies of what you'd like, in the form of attenuation.
So I have two small questions. First one is, how do you guarantee the security of the message? I mean, sometimes the message could be some sensitive information. How do you guarantee the security? I mean, do you use any encryption or something like that in the process?
The question was, how do you guarantee the security of a message if a message contains some sensitive data? Do we use encryption? That persistent connection is SSL encrypted, but remember, the overall design here is not to have state in the message. Don't send, if you want to have something sensitive in that message, you can encrypt it. You can do that with the arbitrary payload. So that's something you can do at an application level. Or don't send anything sensitive down that pipe. Just tickle your application and then have your application fetch its sensitive data directly. That's the kind of design that we've made use of in building our own sync functionality.
Right. So basically, you mean so C2DM is not suitable for the sensitive use case, right?
The question was, Android cloud device messaging isn't suitable for sensitive information. And again, I think that's something that you can work through in your design by using the techniques that I talked about. So that's something that you can control on the application side.
Right. The second small question is, how do you guarantee the authentication? I mean, someone else may be able to steal my registration ID and pretend to be me and register to the server.
The question was, how do you authenticate these requests? How do you make sure that someone else doesn't steal a registration ID? There's two bits of information here. One is the role account that you specify when you create the registration. And we make sure that when an application server tries to issue a message to a registration ID, that the authentication credentials for the HTTP post match that role account. So it's up to you. I mean, it's a password. It's something that you should keep safe or secret on your own. Don't start giving out that password, for example. That's why you can also use a role account. And the second thing is there's a per app, per device registration ID. And that's also something that your application gets and can send to your server. Don't give that out either. Right? There are two bits of information that you need to send a message to an app on a device.
OK, thank you.
Let's go ahead and see if there's any offline questions, any questions on moderator. I think we answered the first question, which is this requires Android 2.2. Second question, could you discuss the relationship between cloud to device in the core Android SDK and any dependency on Google services? The Android cloud to device messaging API is a Google service that's supported on Android 2.2 devices. A Google account is required on the device. Of course, your application doesn't need to think about or worry about that account. You can use whatever authentication credentials make sense for your domain. But to establish or maintain that connection, a Google account needs to be on the device. So there is a dependency on Google services. The next question was about market, and I think we already answered that. The next question is, what's the data format, or is that also up to us? The data format, if you're going to be sending some payload, it's arbitrary key value pairs that you send in your HTTP post, and you can have those values be whatever you want it to be.
What's the max size of the message, and how long will it last on Google servers before it's delivered to a user, if in case the user is offline?
The question was, what's the max size per message? Max size is 1K. And second question I had a little bit of trouble with, how do we make sure that the message gets to the device?
No, how long will it last on your servers till it's delivered to the user in case the user is offline? What's the maximum amount of time that it can survive on your servers?
I think on the order of weeks, maybe a month, you know.
From the perspective of the server that's generating the message, is it fire and forget, or can it get an ACK back?
In terms, so the question is this a fire and forget request, or will the application server get an acknowledgement back?
Correct.
The application server will get back an ID when it sends the message, and if it gets back that ID, then the message is on its way to a device. There's no end-to-end acknowledgement that comes back from the application. Typically, again, that's something that you do in your own application logic. If you want to have that kind of functionality, when your application receives the message, wakes up, it can talk to your application server and provide that acknowledgement.
Right. Okay, thanks.
You may have mentioned this, but I didn't catch it. Does this work on a device that doesn't currently have service and only has a Wi-Fi connection? Will it go through a home router?
The question was, will this work on Wi-Fi? Yes, as long as you have a data connection, then the device can go ahead and establish a connection with our servers. I mean, you know, it also is you'll need that data connectivity for your application to access data in the cloud as well.
Right. Okay. Thanks.
And I think that's it. Thank you very much.